right. So welcome to chapter 6. Chapter 6 is all about exponential and logarithmic functions. You talked a little bit about exponential functions in Algebra 1, and so we're just going to kind of go a little bit deeper here. And so this is going to be a bit longer in terms of the video because there's just a lot to cover, but then you've got a work day to get all caught up, so it'll be okay. Okay, for this introduction here, I'm going to give you two choices. I'm either going to give you $4 million today, or today, for option 2, I'm going to give you a penny. And then tomorrow, I will give you another penny, doubling your money. And then the next day, I will give you 2 more pennies and doubles your money. And then the next day, I'm going to double your money again, okay? And this is going to happen for 30 days. All right, and so my question to you is, which one would you choose and why? And whenever I ask this question, the class is always split. Some of you guys choose the 4 million for different reasons, but some people choose to choose the pennies. And so let's just summarize our thinking here. Obviously, 4 million is 4 million flat, right? So that's not going to change. But let's see what happens here with these pennies. Okay, so after 1 day, you have 1 cent. And after 2 days, I double your money and you have 2 cents. After 3 days, I double your money and you have 3 cents. After 4 days, I double your money and you have 8 cents. And then after 5 days, I double your money and you total have 16 cents. Okay, and so we're going to continue this pattern here as we go through. And so day 6 will be 32 cents. Day 7 will be 64 cents. Day 8 gives you $1.28. So it takes 8 whole days for you even to get over $1. Okay. After 9 days, you have $2.56. And then you've got after 10 days, you've got $5.12. After 11 days, you're going to have $10.24. Okay? After 12 days, you're going to have $20.48. After 13 days, you're going to have $40.96. Okay? And after 2 weeks, you're going to have a grand total of $81.92. So some of you are thinking, yeah, there's no way this is ever going to reach 4 million. No way, no how. Okay? But actually, if you look at, and I did this ahead of time, but if you look at this, okay, by the third week, you have $10,397 or $10,397.76. So total, it actually works out okay. And then when you get to day 30, notice that on day 29, you only have 2 million only, right? But on day 30, you actually double that money and you get to 5 million. So the better option here is to wait the 30 days and choose the penny option. But I know that some of you just don't. So anyway, so this is an example of something that we say it's increasing exponentially. It's an exponential increase, but more commonly we say that it's exponential growth. That's the term here that I really want you to get used to. Okay, is that it's exponential growth with all of this. Okay, so let's just plot these points so you can kind of see what the graph would look like. So at 0 days, you have $0. 1 day, you have a couple cents. 2 days, it's a few more. 3 days, it's a few more. 4 days, it's a few more. 5 and 6 and 7 and 8, we finally have reached 1. And then when we get to the 9th day, we have $2.50. So we're 1, 2. And then on the 10th day, we've got 5 whole dollars. So 1, 2, 3, 4, 5. And then on the 11th day, we've got $10.24. And on the 12th day, we've got $20. And on the 13th day, we've got $40. And then on the 14th day, we've got $81. So we're somewhere up there. Okay. So when we connect these dots here, you can see that it's what you guys like to call in science a J curve or an L curve. Okay, but in math class we say that that's an exponential curve. All right, so great. Beautiful. Okay, so now let's look at something that's similar but a little bit different. So you guys are all familiar with March Madness, okay? It's a series of basketball games that's held every spring leading up to the NCAA Men's Division I National Championship, and the tournament begins with 64 teams about. I know that there's some other things that go on, but it's about 64 teams, and it concludes with a national champion. In the first round, each one of the teams plays another team in the tournament, and the winner moves on, right? You're familiar with how this works, okay? And the process continues. So after the first round, there's 32 teams left, right? Only half of them move on, only half of them win. So then after the second round, there's 16 teams left. That's a Sweet 16, okay? And then after the third round, there are 8 teams left. And after the fourth round, there are 4 teams left. And after the fifth round, there are 2 teams left. And then after the sixth round, there is 1, and that one is your winner, okay? And so when we describe how the number of teams is changing after every round here, we're basically cutting in half. Okay? We're cutting them in half. Or dividing by 2. Or multiplying by a half. Whatever you want. So this scenario represents what we call an exponential decay. All right, we're decaying exponentially here. So let's make this graph. In the first round here, we've got 64 teams playing. And then after round 1, we've got 32. And then 16. Then 4. Then 2. And then 1. And so if we connect our dots, it makes the same shape, just going the other way. And my graph obviously isn't perfect. Okay? Okay, cool. I'm going to skip this next section just for the sake of the video. Anyway. All right, so we've got 2 things happening here. We can either have exponential growth, which means that we're increasing, or you can have exponential decay. All right? And here's this word asymptote again. I think that I don't know if we've talked about this yet, but an asymptote is a line in which we get really, really close to, but we never ever touch. And so what's going to happen here is with a decay situation, this is going to come down and it's going to get really, really close to this x-axis, but it's never quite going to reach there. Okay, it's going to skate along it and it's going to keep getting closer and closer and closer and closer, and it's never going to reach there. And similarly, that's where this exponential growth function came from. It came from skating on this really thin ice over here, not from 0, but really close to 0, and then it's gradually getting bigger and 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 bigger, and it's going on forever. Okay, so the x-axis is what we call an asymptote. It's never going to touch it, but it's going to get really, really close. Okay. So for exponential functions, an exponential function takes the general form y equals ab to the x, where a cannot be 0, okay? Because if a is 0, then this whole thing is 0. Well, then that's not exponential at all. The whole thing is just 0, okay? B has to be bigger than 0, okay? Because if b is negative, it creates what we call an oscillating function. We're not going to talk about those. Just understand that b cannot be negative, okay? And then b also cannot be 1, because if b is 1, 1 to any power is 1. So then we don't have something exponential. And a is what we call the initial amount. And b is the growth or the decay factor. Okay? So the first thing we're going to talk about is graphing exponential functions, and we've got this handy-dandy graphing calculator here, so we're going to use it. So we go to y equals, clear out whatever you got in there, and you've got 2 to the power of x. Okay, that's what we're going to graph first. Sorry, I know my brightness is just a little bright. Hold on, let me turn my brightness down. There we go. Okay, anyway. Y equals 2 to the x. Okay, so now we go to the table. Okay, and if you notice, you get really, really small decimals, and the smallest one that's probably easiest to plot is this negative 2, 0.25. So this is negative 2, 0.25 is 1/4, okay? And then the negative 1 is 1/2. The 0 is 1. The 1 is 2. The 2 is 4. And the 3 is 8. Okay, so let's plot these. So negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. Okay? And like I said, this is going to go all, like it's going to continue to get closer and closer to that axis, but it's never actually going to touch it or cross it. Okay? That's what the asymptote idea is. So now let's look at what happens if we create a fraction there. Okay? So 1/2 to the power of x. So the biggest one, so this only goes up to 10, it looks like. So I think we should probably start here with negative 2, and that's 4. Negative 1 and 2, 0 and 1. 1 and 1/2, 2 and 1/4, 3 and I believe that's 1/8. Okay, so negative 3, 8, negative 2, 4, negative 1, 2, 0, 1, 1/2, 1/4, 1/8. Okay, so this one's going to come down just like this. Okay. So moral of the story, it just kind of showed you the pattern of what's happening here. Oh, sorry, you can't see. I apologize. Okay. All right, so let's now look at this. Knowing that those two are the examples that we're going off of here, okay, in general, what has to be true of A and B? Okay, so if A is bigger than 0, but B is bigger than 1. So we're talking about this number on the inside. So here it was 2, here it was 1/2. If B is bigger than 1, then we have growth, okay? But if A is bigger than 0, and 0, remember, B has to be bigger than 0 to begin with. But if B is less than 1, or a fraction in between 0 and 1, then you've got a decay situation. Okay? So, cool. Moving on with life. So let's just kind of explore some of that situation a little bit more. So for growth and decay to be exponential, a quantity needs to change by a fixed percent over time. Okay? It must change by a fixed percent, over time. Okay? And so what that means is it just can't change. It's going to be a percentage. It's not like a slope where a slope had the same rise over run. It's a percentage this time. Okay? And so we have here the amount of quantity A of t after t years can be modeled by. Okay, exponential growth here. A of t equals, this is the formula that you're going to use. Okay? And let me explain what these parts are. And these will, by the way, be given to you on your test. Okay? A of t is your final amount of whatever you've got. The A is the initial amount. The R is the rate at which you're changing, but make sure that you make the note that it's in decimal form. Okay, it can't be in a percentage. It needs to be in a decimal form. Okay? And T here, T is the time. Okay? All right. And for decay, it's going to be the same thing. So I'm just going to write the formula and not write what they mean. But instead of a 1 plus r, you're going to have a 1 minus r because things are going down. So when we're talking about this b value, this growth or decay factor, okay, so this is the growth factor, this is the decay factor, this is the growth rate and the decay rate. Okay, it's all depending upon 1, the number 1. If you're over 1, you're going to be growth. If you're under 1, you're going to be decay. Okay? And so let's look at a few examples so we can kind of practice that. The value of a car in thousands can be approximated by the model y equals 25,000 times 0.85t, where t is the number of years since the car was new. Okay? So tell whether the model represents exponential growth or decay. All right, well, so what you need to understand, first of all, cars depreciate, okay? They don't grow in value. But also, if you look here, this number on the inside, that is less than 1, which means that we subtracted a rate from 1. And so this is an example of exponential decay, okay? And so then it says, identify the annual percent increase or decrease. Okay, so if we know that it's decay, we know that what's on the inside is equal to 0.85, but we know that what's on the inside is also equal to 1 minus r, then those two things must be equal. Basically, I'm asking you how far away from 1 is 0.85. And so if we solve for r, we subtract 1, you're left with negative r equals, and then 0, hold on, I lost it. 0.85 minus 1 is equal to negative 0.15. And if you divide both of those by negative 1, you get a positive 1.5. And that as a percentage is 15%. So this car depreciates by 15% per year. Okay? So if we're depreciating at that rate, okay, we have the equation here, A of t equals the original value of $25,000 times 0.85 to the power of t. That's what we got to begin with, okay? But I want to know when, so we're looking for the time that the value of the car will be 8,000. So we want the end value to be 8,000. We've got 2,500 times 0.85 to the power of t. And if you notice, the variable in which we need to solve for is in the exponent. And we haven't learned how to do that yet. And so that's kind of what this entire chapter is going to get us to do, is learn how to solve when you've got a variable in the exponent out there. Okay, but for now, anytime that you have something to solve and you don't know how to solve it, you can always go to your graphing calculator. Okay, and in y1, we're going to plug in 8,000. And in y2, we're going to plug in this other one, 25,000 times 0.85 to the power of x. So we've got both of our sides, and I just want to know when they're equal. Well, they're equal when they cross. And when we plug this in, we're not going to see anything, and that's because our numbers are really big. Okay, so I need to change my window as soon as it stops thinking. Okay. And I'm going to let my x minimum be 0. And my maximum, okay, think about a car. I'm probably going to own a car 20 years-ish. Okay. And the y's is the value of the car. And it starts at 25,000. So I'm going to go up to 30,000. And when we do that, we get this. And so what we're looking for is where those two are equal, and they're equal right here at the intersection. If you remember, you can find the intersection by going second, trace, intersect, getting really close to the first curve. It jumps to the second curve, and then you find your intersection. Okay, and so the t value there is 7.01. So it takes about 7 years for our car to go from $25,000 to $8,000. That's probably about accurate. Yeah, it's about accurate. Okay, so now let's look at an example of growth here. In 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by 1.18% each year. So write an exponential growth model to give the population y in billions after 2000. Okay, so y equals, we start with 6.09 billion. We're growing, so 1 plus, at a rate of 1.18%. Now to change, remember, this has to be in decimals. They gave you a percentage, but you need a decimal. So you need to go over 1, 2. So you actually add 1 plus 0.0118 as a decimal. Be careful with that, to the power of t. So that answers the first question. That's the growth model. You could combine these if you wanted to, but you do not have to. Okay? So you combine those if you want. But anyway, so that's the model. And then it says estimate the world population in 2005. So they gave us a time this time. But watch out, because t is the years after 2000. So t is going to be 5, not 2005, but 5. So y equals 6.09 times 1 plus 0.0118 to the power of 5. Okay? And so if you plug that into your calculator here, okay, 6.09 times 1 plus 0.0118 to the power of 5, that gives you 6.46-ish. 6.46 billion people in the world in 2005, according to that model. Okay? So now let's estimate the year. So now we're looking for the time when the world population is 7 billion. So now I gave you the y value of 7 billion. I know that my model is 6.09 times 1 plus 0.0118 to the power of t. And now we have to solve it just like we did this other one, where we know that that's 7. We know that that is 6.09 times 1 plus 0.0118 to the power of x, okay? And we go to our graph, and we're not going to be able to see anything because the window is all messed up. And so once it's done thinking, we'll change that. And it's still thinking. Okay, so let's change the window. So remember, this is in billions. So the time is just going to go from 0 to 7. Or we don't know that actually. Let's just guess. Let's keep it 20, okay? And the y's are talking about the number of people, but in billions. And so I want to know when it's 7. So if we went up to 10, we would be okay. All right, then we go to our graph. So we're here, okay? And we're looking for that intersection. So second trace, intersect, and it's already there, it's already there, it's already there. Enter, enter, enter. And we're looking for this x value here at 11.87. So we're approximately 11.87 years, but it's asking estimate the year. So we need 11.87 years after 2000. So it's about going to be the year 2011 when this occurs. You could have put 2012. I probably would have accepted it, but it's in the year 2011. Okay? Ish. Okay, cool. All right, moving on. All right, so the last kind of topic we have to work on here is compound interest. If any of you have a bank account, you actually have compound interest in your life. The bank actually gives you an interest fee when you have a bank account there. And so here's the formula that they use. And it looks very similar to the one we just looked at. A equals P times 1 plus R over N to the N times T. So we've got a couple other things here. Again, I will give this to you on your test. But A still stands for the total amount. P still stands for, we call it the principal, but it's the initial amount. Okay, still the same thing, the initial amount. The R is the rate. The N values here, that is the number of times we compound per year. Okay? Or I don't want to say per year. I'll just say per whatever the time is that we are talking about. Most of the time it's the year. Okay? And the T here, that's the time, okay? And this, I think, is going to make a whole lot of sense when we do this here example, okay? So the example is you deposit $9,000 into a college account that pays 1.46% annual interest, okay? Find the balance after 3 years when the interest is compounded quarterly and daily. Which one gives you more money? Okay, so we're going to do both of them. So let's just do the quarterly first. So what that means is you start with $9,000, okay? We're growing in amount. And the rate is 1.46%, which is 0.0146 as a decimal. And then N is the number of times we're compounding a year. Well, if we're compounding quarterly, we're compounding 4 times per year. And then we've got N times the time they want us here is 3 years. Now the cool thing here is that we can plug all of this into the calculator. Just be careful how you do it. Okay, so let me show you what it should look like. 9,000 times 1 plus. This needs to go in a separate parentheses, 0.146 divided by 4. Close both of the parentheses, then raise it to the 4 times 3. That's what your calculator has to look like. So be careful when you're doing this, okay? So the final answer here is $9,402.21. So that's pretty good. If you're earning $402 in a year, that's pretty awesome. Okay? Now let's look at what happens if we compound daily. So we still start with $9,000. All right, we still got 1 plus 0.0146 divided by, but this time daily. We're going to pretend it's not a leap year and that there are 365 days in the year. So we've got 365 times 3. Okay, so here we go. We've got 9,000 times 1 plus, parentheses, 0.0146 divided by 365 to the power of x. Oh, not x, sorry. 365 times 3. And that gives you $9,402.95. So you end up about the same here, okay? You don't end up, too crazy in either direction. You end up about the same. And so we're going to kind of explore that more. We're going to see a different kind of interest in the next section. But yeah, so you're now ready to start 6.1 Big Ideas. Let me know when you have questions, and good luck.